This is the universe. This is everything. And what we're going to be talking about for the rest of the year is all of this stuff that's in the universe and what it's made out of. So I wanted to start off by showing you something where we start off by looking at the really big objects and think about what these things are made out of. So we have galaxies, which are collections of stars. We get into nebulae, which are giant clouds of gas and dust. And then we get down to the size of our solar system, and some of the biggest stars. VY Canis Majoris is the biggest one we know of. We get into some smaller stars here. Then we get to the planets, Neptune and Uranus, and there's Earth, and you can see the size of the United States compared to the entire Earth, and Mercury, some of the moons of Jupiter, Italy and Texas, the Grand Canyon. There's Central Park in New York and some of the biggest buildings. Some of the larger animals, and then, well, there we are. So here's the things that are smaller than you and me. Square inch, ants. Now we're getting into some really small sizes. The thickness of a human hair, a skin cell, the nucleus of a cell, the wavelengths of light, viruses. There's your DNA. Now we're getting really small, down to the size of atoms and molecules. There's a hydrogen atom and a helium atom, and you may know that things are made up of atoms, but what are atoms made out of? Here's the nucleus of an atom. There's some of the parts that an atom is made out of, protons and neutrons. But what are those things made out of? Well, there's quarks, up quarks and down quarks and strange quarks and charm quarks and bottom quarks, neutrinos, more quarks, more neutrinos. Now we're getting really tiny, so I'm really interested in what's all the way at the end here. What is everything made of? What is all the stuff in the universe actually made of? Finally, at the end here, we get down to what's called the Planck length, which is the idea of the smallest possible length that you can have, and quantum foam and string. Well, these are all some ideas. We don't know too much about this size scale, but this is what we're going to be talking about for quite a while now, what things are made out of. Don't forget that red slides are where you have to take notes. You should have your notes handout ready to go. Don't forget to look for the owl and let me know where he is. And remember to fill in all of this stuff that you see here. So what we're looking at here, let me explain what's in the background first. In the background is a really important picture. In fact, I would even be inclined to say that this is one of the most important pictures that human beings have ever took. So this picture that you see in the background there is what's called the Hubble Deep Field Image, and that is a picture of what we see when we point the most powerful telescope that humans have ever made at a portion of the sky that for every other telescope basically looks blank. And this is the image that came back when they did that, and every single little speck that you see on that image, from the big blobs to the tiny, tiny little dots, every single one of those is an entire galaxy with hundreds and hundreds of billions of stars in it. And so we could think of this as being one of the biggest pictures that humans have ever taken of stuff. matter, things. And what I want to talk about in this video is it has to do with the idea of what exactly is stuff. What is the difference between stuff and what we would think of as the black space in between that stuff, the empty space? Well, so a good starting point is this image that you see in the foreground here, and this you might know is the periodic table of the elements. And this is kind of an interesting one. I really like this one because it actually shows you an example of each one of the elements and gives you the sense that these elements aren't just letters and numbers and things like that, that they're actual real things like gold and iron and oxygen and things like that. So these are basically what we would call the building blocks of all the stuff in the universe. And elements are made of parts, and we've learned about some of these parts like electrons and protons and neutrons, and they're all kind of categorized by how many of those little building blocks they have. So that's basically more or less what stuff is made out of, and all of these things that you see here are just big, huge collections of this stuff. And in fact, in these stars, this is where all of these different elements are made. So in stars, basically, we start off with things like hydrogen, this first one here, and helium, this guy over here. And stars basically squish them together and make all of these other guys that you see, these things, all of these things that you see, all of these other elements on the periodic table are made in stars, and that includes the elements that you are made out of, because you are made of all this stuff. And in fact, I'd like to show you an interesting set of graphs here. You can think of them as graphs. So here is the periodic table that I showed you with all the elements on it. And if you look at these other versions of the periodic table here, basically we have all of the same elements on here, but the size of the dot tells you how much of that element is in the universe, in the case of this one, in the Earth, in the case of this one, and in you, in the case of this one. And although they're not all exactly the same, I think one of the interesting things that you see here is that they are all pretty darn similar, that the amounts of things in the universe, like there's a lot of hydrogen and a lot of helium, and there seems to be a lot of stuff kind of in this area here, right? And not much stuff in the rest. Well, if you look at the Earth, you see that there's a lot of stuff in this area as well. And if you look at, well, there's a lot of stuff in this area as well. And so you could kind of make the conclusion here that although they're not all exactly the same, that the universe, the Earth, and you are all made up of more or less the same stuff in more or less the same amounts. And that kind of makes sense, because if there's a lot of certain things in the universe, then you would expect things in the universe to be made up of a lot of that stuff. So, and that's how it turns out. So the interesting thing here is that all of these things on this periodic table, all of the stuff here is basically created in stars, and then those stars explode, and eventually those same little atoms, those same little elements wind up in you. So the atoms that you are made out of were once in a star. I think that's probably one of the more interesting things that humans have ever found out. I find that amazing that the stuff that I'm made of was once in a star. Now, when we talk about matter, this is some delicious looking matter here, we need to think about what it is that makes stuff stuff. So let's start off with a fairly simple explanation here. So matter is anything that has mass and takes up space. I would like to describe it as what we would normally call stuff. So this elephant certainly takes up a whole lot of space, right? And it definitely has mass, and we can see that mass as the weight that it is pushing down on this car. So that's the basic definition of what matter is. But we have a word in there that we need to go into more detail about. So what is mass exactly? Well, we've talked about this idea of mass before, and mass is, in a simple way, is basically the amount of stuff that something is made out of. And we can kind of measure that on a scale like the one you see in this picture here. And so there is less rock stuff over here, and there's more rock stuff over here. And so we would say that there is more mass on this side of the scale, and that's kind of what makes that scale tip down this way. And in fact, it's a combination of the mass and gravity's effect on that mass. So we can get to this idea that mass is sort of the amount of stuff, but it also has to do with the way that stuff behaves in the universe. So let's talk a little bit more about a bit more of a complicated way of defining this idea of mass. So what do we mean that something has mass? What exactly is that, and what's the difference between something that has mass, and are there things out there that don't have mass? Well, when you think of mass, I want you to think of the idea of inertia. And we've talked about the idea of inertia, right? Like this boulder here has a lot of inertia, which is why Indiana Jones is so afraid of it. And the idea of inertia is that it behaves in a certain way. And what I mean by that is that it resists a change in movement. And the more mass something has, the more inertia something has, the more it resists a change in movement. And we can think of that, and that's what we call the idea of inertial mass. The idea that the more something seems to resist a change in movement, the harder it is to push it, or the harder it is to stop it, the more mass it has. But what about light? Does light have inertia? Does light have mass? Well, okay, we've kind of discussed this, and we understand that this boulder over here is made up of what we would call particles, these little guys in here, particles like protons and electrons and neutrons. But we've also learned that, at least in some ways of looking at it, that light is made of particles too, and we call those particles photons. So here's the thing, though, if it's made of particles, do those particles have mass? Does light have inertia to it? Can it speed up or slow down? Well, the answer to that is no. Light actually always moves at the same speed. And in fact, the only difference between these type of particles that have mass and have inertia and these type of particles that do not have any mass and do not have any inertia is really just how fast they're moving. And that's kind of a weird conclusion to come to, that the speed that you move at affects how much stuff you're made out of or how much mass you have. But this is actually something that this guy came up with, Albert Einstein. You know who he is, and this is really at the heart of what this famous equation, E equals mc squared, what that really means. Notice that we have E on this side, which stands for energy, and we can think of that as the sort of as these guys here, right? Light is a type of energy, right? But on this side we have M, which stands for mass, and that's these guys over here, but in between them we have an equal sign. Now the c squared, that's the speed of light squared, but don't worry too much about that. That right there, big number, all you have to know. So the key thing here is this equal sign that's in between them. That really is kind of the mind-blowing part of this equation, is that equal sign, because the idea is that energy and mass are really just two different forms of the same thing. They are equivalent to each other. They really are the same thing. And so the only difference between something having mass and something not having mass really just has to do with how fast it's moving. As you move faster and faster, some of your mass actually becomes energy. And that's what this equation means right here, that energy and mass can be converted one into the other. And part of that is just the idea of how fast you're moving. And so as you approach the speed of light, as you move faster and faster, your mass turns into energy to the point where when you are actually moving at the speed of light, you become 100% energy, and you no longer have any mass and you no longer have any inertia. And that's basically what light is. It's stuff that is moving so fast that it no longer has any mass and no longer has any inertia. In fact, this is what all electromagnetic waves are, is basically stuff that's moving at the speed of light, or moving at the fastest possible speed that you can go in the universe, and therefore all of your mass has changed into energy. I know this is very complicated and it's kind of confusing, but that's really the complicated idea of what we mean by stuff. It's technically energy that's not moving very fast. That's what you're made out of, believe it or not. You are made out of slowly moving energy. So this is a very interesting and very kind of confusing way of looking at it. But like I said, first of all, we can think of it very simply as mass just being the amount of stuff that something is made out of. And then if we want to get a little deeper into that, we can think about that mass as having inertia and think of it in terms of, well, we can measure it by how difficult it is to push something or slow something down. Okay? So this gets us into the idea of the law of conservation of matter. And the reason why this is a good way of getting us into this is because we've already learned about the law of conservation of energy. And as I just told you, even if you didn't quite get all of that explanation there of Einstein and all that E equals mc squared stuff, hopefully you got the idea that energy and matter are both the same thing. They are just two different versions, two different forms of the same thing. And so it makes sense that if you can't create or destroy energy, then you can't create or destroy matter either, because they're both the same thing. So in any physical or chemical change, matter is neither created or destroyed. And we'll talk more about these ideas of physical changes and chemical changes in class. But basically, physical changes, think of that as like breaking something or cutting something in half or something like that. That's a physical change. A chemical change is when we actually do a chemical reaction. So you could think of, like, for example, lighting something on fire. That's more of a chemical change. But in either one of those situations, when we change something by breaking it into smaller pieces, or when we change something by doing a chemical reaction or lighting it on fire or something like that, you do not actually create or destroy any matter. And I know this might seem a little confusing, especially this one, because you think, well, when I burn something, aren't I destroying matter? But we'll talk about that in a second. So matter can be changed from one form to another, but it can't be created or destroyed. So a good example of this would be, say, some wood, and then you light it on fire. And you might think, well, after you light it on fire, isn't the wood gone? Haven't you destroyed it? The key thing to understand here, though, is that technically the atoms that the wood is made out of, all these little parts, these little wood atoms, wood molecules in here, they haven't really gone anywhere as far as the universe is concerned. They haven't left the universe. Some of them may have gone out the chimney in the form of smoke. Some of them might be left over at the bottom of the fire in the form of ashes, but all of those atoms still remain in the universe. They have not left the universe. So all of this stuff, it just goes to different places. That's the best way to think about this. Whenever you change something by breaking it down into smaller pieces, or by burning it, or doing a chemical reaction or something like that, all of the parts that were there to start with are still there. You've just moved them to a different place, but they're still in the universe. So all of the stuff, the atoms that were made up, that this wood was made out of, well, they have become the energy of the fire. Part of them became that, like E equals mc squared. Part of them became smoke, and part of them became ashes, but they still exist. So the amount of atoms in this pile of wood is equal to the amount of atoms / energy, matter and energy combined in the fire, the smoke, and the ashes. But we can even take this a little bit further. So let's think about the beginning of the universe. This is where all matter and energy started. Particles started joining together to form things like atoms. Gravity started attracting those things together to form planets, and sometimes so much matter gets squeezed together that you create a fusion reaction, and that's when you get stars and they release energy. And then plants use that energy to grow and do photosynthesis, and all of that stuff goes into this plant, right? Stuff from the sun, stuff from the earth and the earth's atmosphere all go in to make this plant and make this plant get bigger and bigger and bigger, right? And then when you burn that wood, you're taking all of the energy from the sun and all of the stuff from the earth, from the soil and the water and the air, and you are just returning it back to where it was. You're just putting the light that is coming out literally is heat and light from the sun that was just stored in that plant for a long time. And all of those smoke and ashes, well, they're just going back into the atmosphere and back into the ground where they first came from. It's all this big recycling project of the universe. That is the law of conservation of matter. It is the idea that stuff in the universe, there is no new stuff that's created. Stuff does not leave the universe. It just gets recycled from one thing into another. You can think of it as atoms clumping together and unclumping. That's what atoms do in the universe. They clump together for a while, and then they unclump. So, what's the difference between these things? Now, okay, I know what you're thinking. You've already heard this before. You know the story. This is states of matter, right? We have solids, we have liquids, and we have gases. And you're going to say, okay, yeah, I know that answer. Solids, liquid, and gases, that's the difference. But that's not really what I'm asking. I know you guys already know that, but what actually is the difference between a solid, liquid, and gas? Like, how would you describe these? If you were trying to describe this to, say, an alien or something like that could understand what you're saying because for some reason they speak English, but they're trying to say to you, yeah, okay, I get this idea that there's solids, liquids, and gases, but how would you describe the difference if you were trying to tell them what they were? So, I don't know, solids, let's think about what happens when you poke something, right? So if I poke this, right, it's hard, right? But what do we mean by that? Well, what we mean is that when you poke it, it kind of stays the way it is, like it stays that shape, right? But if you poke water, well, it moves around. It kind of moves out of the way of your finger. And gases do that too, maybe even more so. Like you can't even feel them, that they move around so much. So I want you to think about that idea of how would we actually describe, how would we define the difference between those things? I mean, I guess you could say, you might want to say that this ice, well, it's cold. It has something to do with temperature, right? That's cold. The water is kind of medium and the steam is kind of hot, right? But are all solids cold? Like, for example, a biscuit that just came out of the oven. That's a solid, right? But that's not cold, that's kind of warm. So yeah, temperature definitely has something to do with this, but we can't necessarily just say that solids are cold, right? Because they're not all cold, and we can't really necessarily say that liquids are necessarily warm, right? You can have really cold water. So how are we going to describe this? Well, here is how scientists describe it. Basically, we can describe it by describing their shape and their volume. All right. So let's take a look at solids, liquids, and gases and see how they fit into this way of looking at defining them by shape and volume. So the question is, do these things have a definite shape and do they have a definite volume? Well, looking at these different examples of solid objects, I would say that they definitely have a specific shape to them, right? Definitely have a shape. Like this is kind of a sphere shape here, and this is kind of a hand shape here, right? And we can kind of decide, even if you don't have a good word to describe them, they definitely have a shape to them. So we can check that box off. That's good. Do they have a definite volume? Well, if you recall, if you have a regularly shaped object, like a geometric shape, like a sphere, for example, you can measure that volume by doing things like length times width times height and stuff like that, or, you know, pi r squared or those kind of things, right? to get the volume of a regularly shaped object. For an irregularly shaped object, we can also get the volume by putting it in some water and seeing how much that water rises. Remember, that's called water displacement. So they definitely have a shape, and they also definitely have a volume that we can measure, and it is a specific volume, and we definitely know what that volume is. We can measure it. So it seems like we can check off both shape and volume for solids. What about liquids? Well, let's look at the shape part of this. So when this is in this container, it seems like it kind of takes the shape of the container, right? Like it probably kind of bubbles out at these little bubbles. It follows the shape and lines of the container here. And when it's in this glass, it takes the shape of the glass, right? So this does not really have a definite shape to it. And especially if we look at this part here, right? This shape is kind of constantly changing and moving around and doesn't seem to have a very specific shape to it. So shape, no. Liquids do not have a definite specific shape. What about volume? Do liquids have volume? Well, of course, we can measure the volume with a graduated cylinder, right? We look at the bottom of the meniscus, you should know that word, and we can read the volume of that. So they definitely do have a definite volume. And so to just give you a little bit more about that, I would like to show you a little video clip here of liquids taking different shapes. All right, now let's think about the idea of whether gases have a shape and a volume. So this is basically representing some air that's moving around here, right? Gases, and blowing on this dog. So does air have a shape? Do gases have a shape? Well, you've probably seen gases kind of moving up and wafting into the air and stuff like that, and they don't really seem to have a shape. It's kind of like the liquid that was pouring into the gas. They kind of take whatever shape and kind of move around, right? So I don't think they have a real definite shape. What about volume? Well, I want you to think of the idea of taking a straw and drinking some water out of a glass, and what happens. Okay, so when you have liquid in a glass and you take some of it out, the level of the liquid kind of goes down. It doesn't take up the whole glass anymore, right? Now I want you to think about, if you take a deep breath right now, does the same thing happen in your room? Does the level of air go down a little bit? In other words, is when you take a deep breath and suck some of the air out of the room, does the air kind of go down from the ceiling? Is there a little space near the ceiling where there isn't any air? I think it's pretty safe to say that we all know that that doesn't happen, right? So you can't suck the air out of a room and have it go down like water in a glass. So basically, whatever air is left in that room after you take a deep breath, that air will kind of spread out and fill up the entire room. So it will have the volume of whatever container it is. So it doesn't really have a definite volume. It's not like that hand that you can put in a box and it'll just stay the shape of the hand. It kind of takes up whatever volume of container it's in. So it does not have a definite volume. All right, so states of matter. We have solids. They have a definite shape and a definite volume. So you can think of solids as like this, and obviously they don't have real springs in between them, but the springs represent kind of the bonds between the atoms, that these guys are stuck together, and that's what makes solids solid. It's what makes it so that when you poke a solid, as I said before, the atoms don't really get out of the way for you, they stick together. So I'm going to show you a little video clip here, and this is a clip of water freezing, going from a liquid to a solid. And what I want you to notice is the movement of all these little particles here, and how, as it starts to freeze, how they all kind of stick together and become rigid. Okay, so liquids, they have a definite volume but not a definite shape. And that's because liquids, the atoms in the liquids are all able to kind of freely move around. They're not stuck together as much as they are. So this is kind of what liquids look like. And these are little H2O molecules. There's your two H's, H and H and the O. We'll learn more about that later on. And so these are little water molecules, and they can all kind of freely move around and kind of flow against each other and move around each other. And that's why when you poke it with your finger, they move out of the way. Gases have no definite shape and no definite volume. They will take up the shape and the volume of whatever container you put them in. They all move around freely and bounce around every single edge and take up all of that volume and all of that shape. All right, this is basically what gases look like. They can all completely freely bounce around. When you look at soda, for example, this is basically, so if we look at like a soda bubble like that, or a soda bubble right there, the little bubbles that are in the soda, this is kind of like what it would look like. Here is the boundary right here between the liquid of the soda and the inside part here of the gas bubble. Okay, so here's the liquid, and you can see that they can kind of move around, but they're close together, right? The atoms in a gas, in the little gas bubble, are all bouncing around like crazy everywhere. They're going every which way. And one thing to notice here is that they're not only spreading out more, but they're also moving faster. And that's kind of why they spread apart more. And this gets us into that idea of how temperature and how temperature plays a role in solids, liquids, and gases, states of matter. So to make sure you got this, what I would like you to do is make a little check mark, okay? So for solids, do they have a definite shape? If they do, put a little check mark there. Do they have a definite volume? If they do, put a little check mark there. And same thing with the rest of them. I'll give you a second to do that. Go ahead and check off those boxes. All right, are you done? How about now? You done yet? Okay, you're done? There's the answers, right? Solids have a definite shape and definite volume. Liquids only have a definite volume. Gases have neither. So we're done, right? Solids, liquids, and gases, all set. That's all the states of matter. Oh, there's one more. Plasma. Okay, so plasma is an interesting one. And note that plasma is a state of matter. So just like we could say that water can be a solid, liquid, or a gas, and that we would have liquid water, plasma is not a type of stuff. It's a state of matter that stuff can be in. So pretty much anything can be, if you heat it up enough, can become the state of matter that we would call plasma, just like pretty much anything can become a solid, liquid, or a gas. So plasma is ionized gas that emits electrons. My guess is that sentence doesn't mean a whole lot to you. What it means is that it has been heated up so much that the atoms are flying around so fast that their little electrons get knocked off and they go flying around. That's basically the idea. You have free electrons just kind of flying around because the atoms are moving so fast that they basically break themselves. Interestingly, plasma is by far the most common state of matter of things in the universe because stars are in that state of matter. Stars are so hot, stars like this is the sun is a star, and stars are so hot that they are in this state of matter that we call plasma. So, and that makes up about 99.9% of all matter in the universe. By the way, the word normal is there because that doesn't include the weird kinds of matter like dark matter. But anyway, that's beside the point. Plasma is the most common state of matter for stuff to be in the universe. It just doesn't necessarily happen to be the most common state of matter for things to be in on Earth because Earth is a lot cooler than stars. So that makes only 0.1% of stuff in the universe is in the state of matter that we call solid, liquid, or gases. Interesting fact. All right, So this gets us to the idea of how things become solid, liquid, or gas, how we change from one to the other. So this is what we call the kinetic molecular theory. And we've kind of talked about this in the past, and all of these words here should be familiar words to you. So kinetic, you know what that means. It's movement, right? Molecular, that's molecules. You might not know exactly what those are, but you will shortly. That's just little groups of atoms. And this is a theory, meaning it's very well tested idea that we have never found any evidence to the contrary of this. So basically what this means is that molecules are in constant motion and that this motion is different for the three states of matter. And when I say different, basically I mean that we're talking about the speed of this motion, that basically as you go from one state of matter to another, from solids to liquids to gases to plasma, you are just simply increasing the speed of the atoms and the molecules that substance is made out of. So states of matter are, what's that one? Solid. What's that one? Liquid. That one? Gas. And last but not least, plasma. So the idea here is that you have the slowest moving atoms and molecules here and the fastest moving atoms and molecules here, and that's just a matter of heating up these substances. Remember that heat is just a measurement of how fast the atoms are moving, so the more you heat something up, the faster they move, and that's how we get something to change from one state of matter to another. But you already knew that, right? You knew that in order to make something go from a liquid to a solid, well, what do? You put it in the freezer, you make it cold, right? So that's basically the idea here. So solids have stronger bonds between them, liquids have weaker bonds, gases have no bonds between them, and plasma goes through this what's called ionization. And I'm introducing this word ionizing or ions to you right now. We'll learn a lot more about that in the future, but basically what that means is when electrons get knocked off of an atom. All right, so there you have it, matter. We learned about matter is anything that has mass and takes up space, otherwise known as stuff. We learned that in any physical or chemical change, matter is neither created or destroyed. This is the law of conservation of matter. Matter can be changed from one form to another, but matter is never created or destroyed. We learned about the states of matter. Solids have a definite shape and a definite volume. Liquid has a definite volume but no definite shape. And gases have neither one of those things. We also learned about plasmas, which are basically a state of matter in which the electrons get knocked off of the atom. And we also learned about how substances change from one state to another, and this is known as the kinetic molecular theory, and it tells us that molecules are in constant motion and that this motion is different for the three states of matter, and basically that it is the movement of atoms is slow for solids, a little bit faster for liquids, a little bit faster for gases, and even faster for plasma, and we will talk all about this stuff in class this week, and I will see you then.